Hello, I'm Youngjae Kim, and today I'm going to talk about our recent work for LART. And this work is in collaboration with the following collaborators, and their names and their portals are listed on the slide. And currently, Galen Shipman is with Oak Ridge Los Alamos National Lab. And this is an outline for my talk, and after I present some background and motivation, and I'm going to talk about our design and implementation for LART. And one of the biggest big data challenges is the storing, retrieving, and managing data. In a science domain, the amount of data produced every year has exponentially increased. Department of Energy's data centers, for example, ALCF and OLCF and NERSC are projected to produce 1 exabyte of data per year by 2018. On the other hand, coupling data is to combine two different data sets physically stored on different institutions to use for big data analysis. For example, there are many interesting examples for coupling data, and some scientists may run their climate simulations at ALCF and OLCF, and they may want to validate their simulation output with actual climate observation data set stored at ORNL data centers. Unfortunately, data sets do not exist in isolation, so that data movement between multiple organizations is necessary and required, and data movement cost is not cost-free. ESNet is the DOE's energy science network infrastructure to connect between multiple DOE facilities. With network technology improvement, ESNet has currently deployed 100 gig Ethernet, followed by 400 gig Ethernet, projecting 1 terabit per sec of network capability established in the near future. However, this network improvement only contributes the network data transfer rate, and data sets are still stored at slower storage systems. Therefore, when taking out data from centers to other data centers outside, many problems exist within the data center. Oak Ridge Research Computing Facility has hosted the fastest supercomputers in the United States. As the storage systems, the spider parallel file systems, which runs lost file systems, has been deployed to provide a petascale storage systems for Titan. However, this petascale storage system is a shared storage system for multiple clusters. And analytic clusters and visualization clusters and other computing clusters share the parallel file system with Titan supercomputers, so that when they access the parallel file systems, they can contend for the PFS. And I/O contention can happen on multiple layers of the PFS file systems. And it can happen network layer, and it can happen file server and disk drives. And when transferring data, because of this contention, the PFS can become the bottleneck for data transfers. So the problem is that the network bandwidth is becoming higher than I/O bandwidth to PFS, and the PFS I/O bandwidth on DTN node is underutilized, so that data transfer node is a focal point for impedance mismatch between the fast networks and the relatively slower storage systems. Unfortunately, even worse, the PFS bandwidth is underutilized with various reasons, such as I/O contentions with different co-located applications and within I/O thread of applications. A key question that has been raised to answer is how to improve the underutilized PFS bandwidth on DTN node for big data transfers. In order to answer these questions, we proposed a LART, which is Layout-Aware Data Scheduler. In general parallel file systems, there are multiple different parallel file systems: Lustre, IBM GPFS, and Panasys file system, and PBFS, and Chef too. Since we focused on Lustre file systems for parallel file systems in the rest of our work, so let me briefly talk about Lustre file systems. And Lustre file system is composed of two types of servers, and one is the MDS, and which is the metadata server that holds the directory tree and stores the metadata information about files except for file size. And OSS is object storage server that manages the object storage target and holds stripes of a file for file contents. And for normal I/O operations, when a Lustre client open a file for normal I/O operations, it sends the file open request to MDS, and MDS returns with the metadata that contains the information of the location of object of a file. And then after that, Lustre client make output connections to file servers for normal I/O operations. And the observation that we have from this parallel file system is PFS is used as a single namespace to client. However, it is not a single disk. It is more complicated organizations within the parallel file systems. That is the combination of the arrays of multiple disks with multiple servers. PFS has been designed for parallel I/O operations. However, traditional data transfer tools do not fully utilize the available parallelism available on the PFS for I/O operations. So we call this is a traditional file-based approach, and which is ignoring the underlying file layout on the parallel file systems. And for example, what happens, a complete file can be assigned to a thread in an application for file transfer. And this thread can work on the file until the entire file is read, so that multiple threads can interfere each other when they are accessing the same disk. So here are an example. There are three files, and these three files, A, B, C, are striped over multiple disks. And suppose a thread of these applications reads a file C, which spread their stripes on OSD2 and OSD3. And suppose the thread 2 of this application read a file B. And what happens? They can contend for the same object storage target, which is OSD3. So by that, due to these contentions, what happens? Their thread application runtime can slow down by up to 25%. And another example that can happen in a traditional file-based approach is, since it ignores the underlying file system layout, so that a multiple thread can work on a single file. So even those threads work on different stripes of a file. However, the parallelism that can be achieved with this approach can be limited by a stripe width of a file in the parallel file systems. The same example we have, and this example is the 4 threads are assigned to work on different stripes of a file. However, what happens, each thread 1 and thread 2, can contend for object storage target 1, and thread 3 and thread 4 can contend for disk 3. So that because of these contentions by multiple threads to access the same disk, each thread can slow down by up to 50% based on the theory of conflict. Existing bulk data movement software include Greedy FTP and BBCP. And Greedy FTP, as you may all know, it is part of Globus Toolkit, and it requires a Globus Toolkit installations for use. However, not many DOE facilities have installed this Globus Toolkit, so that it is very inconvenient for scientists to use to move their data. And it's implemented to support the multiple I/O thread for parallelism. However, it implements a file-based approach. And BBCP is the most popular data transfer tool that has been deployed in multiple data facilities for data movement for convenience reasons, not for performance reasons. It also implements a file-based approach. BBCP is the tool that we're going to compare our large tool for performance comparison. And RFTP is another file-based approach that has optimized POSIX I/O interfaces. However, it does not fully utilize the underlying layout of files on the parallel file systems. And SCP is a single-thread secure copy tool. And none of these tools are optimized for fully utilizing the parallelism available on the parallel file systems for big data transfers. So that now, why does it happen? Because traditional file data transfer tools employ a logical view of files. On the other hand, the LARC that we proposed used a physical view of files instead of logical view of files. With that, LARC can understand the physical layout of files on the parallel file systems and can understand which file are composed of what object, and can understand the set of object targets that holds the object, and can understand the topology of storage servers and targets. And with this approach, we call an object-based approach, is aware of the underlying file layout of the parallel file systems. With this information, with this knowledge, a thread can be scheduled to work on any object on any disk, so that it can avoid the contentions that could have been happened in previous file-based approach. In this example, 4 threads can be assigned to work on different disks, so that they can avoid contentions on the servers, so that the maximum parallelism, which is 4 in this example, can be achieved, so that none of our threads can contend for object storage targets. Large has 4 design goals. The first goal is to maximize the parallelism on multi-core CPUs of data transport node. Second, it supports portability for modern network technologies. We achieve this goal using CCI, Common Communication Interface API. And third, it takes advantage of the parallelism available on the PFS for improved parallel I/O operations. And third, it implements a hotspot and congestion avoidance algorithms to avoid congested servers. So that ending goal is to have an end-to-end data transport optimizations excuse me, to solve the impedance mismatch problems with, between the faster networks and slower storage systems. And we use the CCI for portability support for modern HPC networks. CCI is a network API for inter-process communications that can abstract out underlying network drivers for heterogeneous network technologies. This is the overview, architectural overview for large. And the left side, the large source, and the right side is large sink. CCI implementation construct endpoints, virtual device, and pre-registered RMA buffers on DRAM. And it implements 3 types of thread. And a master thread coordinates resource access and manages various internal states. And IO thread are actual worker thread to work on reading and writing data chunk. Communication thread posts in a CCI loop and transfer data. And moreover, it implements layer-aware and congestion-aware and NVRAM buffering algorithms. And similarly, large sink implement likewise large source for implementations. This is an example for transferring data and storage. Since the sink has the similar operations, so that I'm going to just simply explain with these examples for large source. Large source implements data structures, and there are OSD queues and as many as the number of object storage targets on the parallel file systems. And there are RMA buffers, and currently 3 slots are occupied on the RMA buffers. And suppose a scheduler master thread points to the object storage target Q4. It dequeues on one item on the bottom from the queue and read a yellow 2 from OSD4 into the RMA buffer. And then delete that item from the queue. And with round-robin algorithms, it moves on to the next OSDQ1 and reads a blue 2 from OSD1 into RMA buffer, and then delete the item from the queue. And now the situation comes at RMA buffer to be full. So now IO thread will go on go into sleep stages, so that it waits until a communication thread after it frees up a RMA buffer full to wake up IO thread. And once a communication thread transfer a block to free one slot from RMA buffer, and all IO threads are waken up and scheduled to work on reading and writing operations. In this example, the thread is picked and read a blue 1 from OSD2 into RMA buffer 4, and then delete the item from the queue, and so on. And large implements a congestion-aware algorithms, and it is intended to minimize the impact of intermittent congestions that can happen on the storage servers. It implements a threshold-based reactive algorithms using a threshold value for determining congested servers, and the number of skips that IO thread can skip over one or more the number of servers. In this example, simulation code are running on Titan supercomputers, and suppose it generate a bunch of IOs to overload some of object storage targets on the PFS, and OSD1 and OSD5 become hotspot. Now, large storage when they transfer the data blocks, and it reads first a data block from OSD0 in this example. And since the OSD0 is not a hotspot, it can simply read as a normal I/O operations. And then next, once it attempts to read a data block from OSD1, since OSD1 is congested, so that it can be detected with a threshold value, which can be greater than the reading time is greater than this threshold, so that it can be detected as a congestion. Now, suppose now it is marked as a busy status. And now suppose the OSD 5 has the same situation, so that it marked as the busy status. Now once it is scheduled to access the hotspot OSD, then simply IO thread is scheduled not to access that OSD and to access the next OSD, which is not busy. Large implement a source-based buffering algorithms for SSDs. And source RMA buffer can be full if the sink is experiencing widespread congestion on the servers. In this example, SSD spaces is mapped on extended memory buffer. In addition to RMA buffer, it can be used as an extended memory buffer to keep data object for transfers. And this examples, in previous algorithms, without these algorithms, the IO thread has to go on a sleep status and wait until RMA buffer is freed. However, in these examples, it can read a data block and put it in the extended memory buffer, which is mapped on SSDs. And it maintains additional SSD queue in addition to object storage target queues. Then once it is freed and on the RMA buffer, SSD queue, the item is deleted and then compute to access the a slot on the RMA buffer. This is our test bed configurations. We used Intel Xeon servers for DTN node, and each DTN node is installed with 2 Fusion IO SSDs, which is configured in a 12-tier RAID. And each DTN node is connected to the PFS, for which we used lost file systems on top of 32 disk drive. And these 2 nodes are connected with IVQDR 40 gig network. This is the validation of our test bed. In order to reflect the real situation where network is faster than parallel file systems, we measured the IO bandwidth by increasing the message size using IB-perp. And as you can see, the IB bandwidth is increasing as the message size increases, and it is about 3.2 gigabyte per sec. For storage bandwidth, it is measured around 2.3 gigabyte per sec for highly sequential large block workload. So that we made sure that the storage server bandwidth is not over-provisioned with respect to network bandwidth. And this is a file size distribution of a snapshot taken from the Spider-1 file systems a couple of years ago. And interestingly, what we observe here is 85% of the files are less than 1 megabyte, and less than 50% of the files are greater than 1 megabyte. On the other hand, the larger files occupy most of the file system space. So that we selected 2 file sizes for 2 different workload. For the big fast workload, we used 101 gigabyte files for a big fast workload, and we used 100,000 1 megabyte files for small files workload. For evaluations, we have a congested environment and congested environment test. For the baseline, this is the evaluation result when a storage server is not congested. For a baseline performance comparison, we show uncongested environment test result. And as you can see from the figure, we observe large show a perfect linear scaling with respect to the number of IO threads, whereas there is little improvement with BBCP. BBCP is implemented using a file-based approach, as I explained before, and where files are transferred one by one, and BBCP uses multiple TCP streams to operate on the same file, so that the bottleneck bottleneck is determined by how the files are striped over the disk drive. We had the similar observations from the test with small file workload, and we also measured CPU memory and CPU memory utilizations, and we observed that large moderately uses system resources for CPU and memory. Next, we show the result for congested environment test. And we used the synthetic workload generator to overload disk servers to happen congested situation on the servers. This result shows to compare our algorithms with storage in conditions with a baseline where there is no algorithm to be implemented. to avoid congested servers. The red bar shows when there is no congested as a baseline for comparison. It is measured around 400 megabytes per sec for throughput. Once the round-robin algorithm is being used, the green bar shows the bandwidth can drop down to around 220 megabytes per sec. On the other hand, blue bar shows the result when our algorithm has been implemented to be used. And as you can see, as we increased, if we used the too high threshold for determining the servers, then it may not detect well the congested servers. On the other hand, if it skips too many hotspot servers, then it may make false positive decisions for detecting the congested servers. And overall, it shows that our algorithm outperforms the baseline algorithm using round robin. And this is the algorithm. This examples to when the source PFS is only congested. And the next experiment is to when sync storage system is congested. And interestingly, the performance impact is significant compared to when source storage server is congested. And we also observed that there are random performance improvement, surprisingly, and we investigate the reason why it happened, and we figured out that the use of the buffered I/O prevented it from accurately measuring the OST's actual level of congestions. We have more experiments because of the time limit. Let me summarize what we have for the rest of experiment we have. And we studied the effectiveness of the use of flash buffering as source, and we observed that doubling the size of DRAM is very expensive, and the same throughput could be achieved using the flash memory, cheaper than DRAM memory. And also we had actual evaluations using DTN node at Oak Ridge National Lab. And in this experiment, we measured transferring data, time for transferring data from one Atlas 20 petabyte file systems to another file systems, Atlas 2. And we observed, similar to the observation we had, large shows up to 6.8 times higher data transfer rate than BBCP. And this is summary. We have identified with this research that there exist multiple bottlenecks along the end-to-end data transfer from source to sync systems, and we developed LART to have optimized end-to-end data transfers. And we also proposed the three algorithms: I/O slicing, an object-based approach, and layout-aware and congestion-aware, and source-based SS buffering. And our vision is to have an end-to-end optimized end-to-end virtual path from any source to any sink, so that we provision to promote collaborative research of scientists between multiple national labs and organizations. This is what I have prepared. If you have any questions, I'm happy to take your question. Thank you.
Yeah, I have a couple questions. First one is, how do you compare and contrast this to the work that's been done with network request scheduling?
I'm sorry, I cannot hear you. Can you speak up a little bit?
Sure. How do you compare and contrast this to NRS work that's been done on Lustre already, the network request scheduler?
I'm sorry, I don't understand your question. How do we
compare and contrast the work that you've done with the work that's been done on the network request scheduler by the Lustre community?
Maybe I'm not familiar with the network schedule optimization in the Lustre community, but I would say this work has using the file layout informations on the parallel file system, so that application level it can be smartly schedule the I/O thread to work on different servers, so that it can avoid congestions. So that I think maybe. My answer is wrong, since I'm not familiar with network optimization in Lustre, okay. But yeah.
And the other question I would have is, what have you done, if anything, related to Lustre eviction? Your assumption within your test bed seems to be that you have a perfectly fine working environment in a large-scale production system like those typical at Oak Ridge National Labs, Los Alamos National Labs, NERSC, NCSA, typically production environments aren't always 100% operational. So you get into situations with either drive failures or luster client evictions with extremely large production environments. Has there been any consideration or work done to compensating for failure within the hardware-software regime?
Actually, this work does not deal with any failure issues, but as you mentioned, Oak Ridge National Lab, despite the fast systems, has shown that there are multiple contentions that can happen from time to time. So that as on the last slide, as I showed you, as a result, we compared large with BBCP on two different fast systems to move between these two fast systems in production environment.
Thank you.
Yeah.
Let's take any other questions offline, and let's thank the speaker. Thank you.